Welcome everybody to this session on the Nobel Prize in Economics 2020. On this picture you see the two Nobel Prize winners. On the left you have Mr. Robert Wilson, this guy here, and on the right hand side you have Paul Milgram. Both of them are at Stanford University. Wilson is right now an emeritus and Milgram is still active. They won the Nobel Prize for improvements to auction theory and invention of new auction formats. And so we at the Department of Microeconomics and Public Economics, we thought it might be a good idea to give you a short glimpse in 30 minutes what these two gentlemen have done. To do so, since they won the prize for theory and for implementation, we also decided to basically split this lecture into two main parts. The first one will be given by Stefan Terstiege on auction theory. And the second part will be given by Rudolf Muller from the BISS Institute and the Department of Quantitative Economics. And Rudolf also met Milgram and might have also some personal stories about Milgram, which will liven up the presentation. At the end, I will say a few words about other contributions of both Milgram and Wilson. And if you have questions or remarks afterwards, we are very happy to discuss them. Before I pass on to Stefan, I want to share this picture with you. So this elderly gentleman is not invading a home, but it's actually a picture of Wilson, whom you might have recognized from the previous slides. And this is during the night, and Wilson is actually ringing the doorbell of his neighbor, and the neighbor is Milgram. So why is he doing that? He just received the news that they got the Nobel Prize, and then you see this elderly gentleman going over, ringing the doorbell of his neighbor at night and informing him that he won the Nobel Prize, but that they could not reach him via phone. Very nice story. If you want, you can also watch YouTube videos on that if you just enter the two names. So, but this is not a popular show right here, so I will now pass on the torch to Stefan, who will give you more content.
Why have a theory of auctions? Well, very many things are sold through auctions. Yeah, we all know Picasso paintings, they are sold at Sotheby's and Christie's. But also most government procurement is done through auctions. For example, if Maastricht wants to have new furniture for its schools, then they must choose the supplier through an auction procedure by law. Or public assets. This summer in the Netherlands, there was a big auction where the 5G frequencies were sold to KPN and other companies that raised over 1.2 billion euros. Now, key topics in auction theory are as follows. First question is probably, which auction format should you use? That depends, of course, on the situation. It will also depend on the goal that you have. Yeah? Probably the goal is usually that you want to have a high revenue. But often one also looks at efficiency. For example, with 5G frequencies, one would like that these frequencies go to those companies who are best able to manage them. Secondly, one also wants to study and understand the bidding behavior in various auction formats. Now, how is this done? The approach is to treat an auction as a game in the sense of game theory. An auction always has very precise rules about how the bidders submit bids and who the winner will be and so on. And this more or less directly gives a game which can then be analyzed with game theory. Yeah, now to understand how they improved the theory, let's first see how it was before then. It started in the 1960s with William Vickery, who studied bidding behavior in various auction formats under the assumption that the bidders' values are private. So that means precisely that each bidder knows the value of the object to himself and doesn't care about what the evaluations of the other bidders are. So an example would be a Picasso painting. The value might be your joy of looking at it, and you don't care how how other people enjoy looking at this picture. Now, Vickrey, he considered standard auctions, so the most common auction formats, like the first price auction. That's where the bidders submit sealed bids, and then the highest bidder wins and pays his own bid. Second price auction, where the highest bidder also wins but pays the second highest bid. And the English auction, which is really this most common auction format, which we all know, where the price is raised by open outcries until all but one bidder dropped out, and that bidder then pays his own final bid. Now, Vickrey had a very surprising result. Although these auction formats are all very different, they all generate the same revenue. This is called revenue equivalence, and it was a very influential result that stimulated a lot of research. But there are two issues. So first, if they all yield the same revenue, then why is it the case that the English auction is so much more common than the first and second price auction? And secondly, this private values assumption is often unrealistic. With a Picasso painting, for example. Certainly part of your valuation might be your joy of looking at it, and that's clearly private, but you might consider it also as an investment. And then you must think about the resale value. And for this, the opinion of others matters to you. Now, in the 1960s and 70s, Robert Wilson moved beyond this private values framework, and he studied bidding behavior in common value auctions. Common value, that means the value of the object is the same for everyone, but no one knows it. Each bidder just has some imperfect information about the value. Since the information is imperfect, you care about what the others think. Example is an oil tract. The value of an oil tract probably is mainly determined by the amount of oil in the tract, which no one knows a priori. However, the different bidders, they all might have some imperfect information, for example, because they might own a neighboring tract. So that's all well and good, private values, maybe they're not really realistic, but is it really important to move beyond private values? So will the results change? And the answer is yes. That's because of the winner's curse. So suppose everyone does know something that matters to you, as it is the case in a common value auction, but it's not the case in the private values auction. Now, if you win, this means the other's information was less favorable than yours, for otherwise they would have bid higher. So given that they all had rather negative information, maybe you were too optimistic and bid too much. So this winner's curse strongly affects the bidding behavior, and therefore it's important to move beyond private values. Now, actually, both private and common values are special. In general, a bidder's valuation, it will or it can depend on the information of all the other bidders. And how the information of other bidders matter to you might also differ from how it matters to other bidders. With the oil tract, for example, it might not only be about the amount of oil in the tract, but also perhaps about which skills are required to extract the oil. If one bidder has information according to which for him it might be difficult to extract the oil, then this might not be so important to another bidder. So private values is special in that a bidder's value only depends on his own information. Common values, whereas everyone's information does matter, it does so equally for every bidder. In 1982, together with Robert Webber, another auction theorist, Milgram tackled this general case. Building on the analysis of Wilson and also prior work by himself, together with Webber, they analyzed the bidding behavior in all the standard auctions. And they also took up this revenue question. Remember, with private values, we have Vickrey's revenue equivalence, that all these auctions yield the same revenue, which was not so much in line with the observation that the English auction is by far the most common auction format. Now they made quite natural assumption concerning the bidder's information, namely that it displays a certain natural form of positive correlation, meaning that if you have positive information, then most likely the information that I have is also favorable. And then they showed these auctions are clearly ranked in terms of revenue. First is the English auction, then second price, and the first price auction is worst. Now, why is this? Consider first the English auction. During an English auction, bidders learn something about the information of others. Namely, they can observe at what prices the other bidders drop out. Now, if you have favorable information, then most likely you will find out during the auction that others have favorable information too. That weakens the bidder's curse, yeah, and the winner's curse, and results in more aggressive bidding. What about the second price auction? During the second price auction, there's of course no learning. Yeah? They submit these bids and then it's over. However, still the price that the winner pays is linked to the information of others, namely to the information of the second highest bidder. So again, if you have favorable information, then due to correlation, most likely the information of the second highest bidder is also favorable. And when you win, then you have to pay a high price because the second highest bidder had a high bid. However, in contrast to the English auction, it's only the information of the second highest bidder that is captured in the price you pay, not also the information of the other losing bidders. Therefore, second price is not so good as the English auction. First price auction, finally, is worse because the information of all the losing bidders is not captured in the price that the winner pays. So, summary. In their early research, Wilson and Milgram developed a very general theory of auctions, which is very useful to understand the bidding behavior and the pros and cons of different auction formats. They didn't stop there. One restriction in all what we have seen was that just one object is sold in the auction. That's not the case in many important auctions like the 5G auction, where many frequencies are sold in the same auction. We will see in the next talk how they took up this more complicated case.
I will focus mostly on Paul Milgram's work. I think he was also much more active in the design of the FCC auction, certainly in the last 10, 20 years. And to understand his contributions to putting auctions into practice, I have to explain to you a little bit what is this additional complexity that comes in heterogeneous multiple objects auctions, and also how they're motivated. As Stefan said already, one of the big motivations were the FCC auctions, where in the 90s of last century, the US Federal Communication Council started to really to use auctions to sell these frequencies. And there's a very nice small graphics that I have taken from the Royal Academy of Science site, Swedish Royal Academy of Science site, with the announcement of the winners of this year's Nobel Prize. And you see here kind of a landscape with, I don't know where it is, maybe Florida or what, with 4 different regions. And so in each of the regions, you have to imagine that there are frequencies for exactly that region that are sold. And it is also likely that there are several bandwidths in each region. So you have maybe 5 different bandwidths, and 4 regions, you have 20 different objects that are sold at the same, that are sold. Now, if you do that sequentially by selling each of these frequencies one by one, you could have the problem that you have that here the blue guy wins just in this area. The second from the right lady, I guess, wins in this area, in that area, and there's a lucky person who wins in all 4 areas. and then maybe after the auction they make a deal, and then so the market is basically the frequencies are reassigned. Now that has a lot of problems, and so one started to think of how can we run auctions how can we design auctions that can sell everything at the same time. Now, why do you have so many problems by selling them sequentially? It is mostly because the valuations for a bundle, so for a combination of different licenses, is not simply additive. So you might have an advantage if you own licenses in two regions, and the advantage might be higher if you own licenses in neighbored regions, rather than here this lady in the yellow and the brown region. So that makes these auctions quite complicated. So basically you want to find prices for bundles at the end, and you want to assign whole bundles. The other thing is, as in the single item auctions, you have also private and common value components in this setting, because the future value of a spectrum might depend very much on how the market for telecommunication market or mobile phone market develops in that area, what kind of new applications are coming up. And if you are very realistic in this setting, you might even see allocation externalities, meaning that it matters for one of the bidders how many frequencies were won by the competitors, because that might determine market share afterwards, economies of scale, and so on. So there are even there's even a valuation for the overall allocation of frequencies that is generated by the auction. So what are the goals then in such auctions? Yeah, in these government auctions, the government usually was concerned about economic efficiency. It was also nice to earn billions with the auctions, but economic efficiency should be the major goal. So you want really to assign the licenses in a way that it is best for the public in a broad sense, in an economic sense of point of view. You also want to omit a winner's curse, like in a single item setting with common values. And particularly because of the bundle pricing, you also want to exclude an exposure problem. And the exposure problem means that if you do single auctions, it could be that this blue bidder has bid very high to win that one, because he hoped that he would also win a neighboring region. But then in the auction for the neighboring region, he lost that auction, and then he's sitting only on that one and paid actually too high price for that. And that is, so he's exposed to an extra risk here. And the other thing, what I mentioned already, you want to discourage as post-trading of the objects. And another issue that you like to have in these kind of auctions is that you generate equilibrium prices. So in a sense, this is a price for the objects, so that at this price, the losing bidders say, oh, it doesn't matter, I wouldn't have won, I didn't want to pay that price anyhow. Now, if you think about a single item auction, like a second prize auction or an English auction, you automatically have this property, right? I mean, in the English auction, the last bidder who wins is basically has won against all the others. So the price that he pays seems not to be of interest. At this price, the object seems not to be of interest for the other bidders. Now, in a combinatorial auction or an auction with multiple objects, it is much more complicated. So the challenge that Milgram and others faced at that time, how can we design an iterative procedure of bidding, temporary allocation of objects and pricing that generates final allocations and prices that get somehow close as possible to all these goals? And iterative was definitely important, because the auction should also be able to signal amongst the bidders valuations, common value components. Now, Milgram then he published a paper in 2000 about that, and with a team probably of other economists came up first with a simultaneous multi-round auction. And that was departing a little bit from the single item auction simply by running single item auctions next to each other at the same time. So just ascending price auctions with minimum increments and all kinds of rules for each individual frequency. But they had then a complicated set of activity rules that connected the auctions to each other, so that you could, for example, not jump into an auction very late only after having observed all kinds of information. So it was a sophisticated design, and it worked quite well. But one thing it could definitely not achieve, it could not get close to to equilibrium prices. And the theoretical reason is that these equilibrium prices based on pricing single frequencies simply does not exist. So even in a private value setting, you can easily construct examples where whatever you price the single items, they will not be market clearing at these prices, even if you put the things on the shelf at these prices. So that made it difficult, and that was also a little bit a shortage of this simultaneous multi-round auction. Still, it was used a lot until I think early of the century, the first 10 years and so on. I think still used at some places, because what you can do next makes it even more complicated. And there is a kind of a trade-off between keeping it a bit simple for the bidders and also for the auctioneer, and sacrificing a little bit in the economic goals, and rather than making it more complicated. Now, and the way to make it more complicated is to run a combinatorial clock auction. And that's also how I met Paul Milgram twice at workshops that I organized. I had him as an invited speaker, and where we discussed basically a lot on combinatorial auctions in the frequency setting, but also in e-business settings and so on. And at that point, also computer scientists became very much interested in that field. And also Milgram started to work a lot together with computer scientists and operations researchers. So what is a combinatorial clock auction? The basic thing is that now bidders can bid on bundles. So they can express a willingness to pay for, in this example, the bundle of the green and the brown area, or the blue and the yellow area, or 3 areas. Now imagine there are many, many bundles. I gave you here 20 objects, so you might have, a lot of bundles already, 2 to the power of 20 bundles, actually precisely. But if you have now 200 objects, 200, 400 regions in the US with 5 licenses per region, you get an enormous amount of bundles. So the bidding is kind of complicated now, and you have to be very careful how to restrict the number of bundles on which one can bid. And also computing the winners becomes much more complicated. There is not a high bid on every frequency, but you have basically to partition the bundles, because you cannot sell 2 bundles with the same frequency in both bundles. And also the pricing is becoming non-trivial. Nevertheless, these combinatorial auctions have then been developed, and they have also been applied, and Milgram is still active in that field, and he is now actually working on the next generation. So there has been recently auctions in California for reselling television licenses to use them for other applications, and then you had to buy first the licenses and then sell them again. So it was a kind of a double auction, a double combinatorial auction, where he made again a lot of contributions to that field. So that a little bit to give you a flavor of the complexity that comes up in this area, and also to give you a little bit of a hint that it can become computationally quite challenging. So I have a few words on Milgram. I don't have so many real anecdotes, at least not anecdotes that I can share, I guess. So I met him 3 times, I guess, and 2 times in a workshop where that I co-organized and where he participated. I know him as a person who is extremely eager to learn whatever is necessary to solve the problems he's working on. He's also certainly a combination of a scholar and a businessman. So he's co-founder of a company, an auction consultancy firm, Auctionomics.com, and you can go to the website and see that there are many economists working with him there, and also computer scientist. And he was always I think he was also driven by the applications, but also he was also consulting a lot and designing for governments, but also consulting companies, bidders in the auction. If you meet him personally, I would say he is a distinguished gentleman of his age. And I always thought he is even a bit shy. So when he gave presentations, he was typically quite nervous up front, the presentation. But it could also be because I think he always would have loved to have 2 hours, but he got then only 45 minutes. And he signaled that a little bit, that it is a little bit too little for him to express what he all has to tell. And one nice thing that he told once, I think at a dinner, that he is always inviting his PhD students regularly, probably not these days, for dinner to his house, and then they're socializing, and everybody is telling about the research that they have been doing and other things. And let me say it like that, knowing him and also knowing others, what they were saying about him, I guess, or I think I'm very sure that he was very, very happy that he finally got this prize.
Right, so as Rudolf said quite a bit already about Milgram, let me also say a few words about Wilson's legacy. And Wilson's legacy would be something that we would like a lot at SBE because we like good PhD supervision. And Wilson is exemplary for that. So here you see Wilson amidst his former PhD students, L. Roth, who worked later on in matching and in designing the matching market for kidneys and for hospitals. Next to him, we have Paul Milgram, whom we have already heard a lot about. And finally, Bengt Holmström, on the right-hand side, who worked on the theory of the firm. And all of these 4 people have now won the Nobel Prize. Yeah, so he has 3 Nobel Prize winners as his former PhD students. Quite impressive. I just want to very briefly mention a few other contributions. Wilson, to me, is most known for sequential equilibrium. So this is an equilibrium concept which basically takes Nash equilibrium and then refines it later on, in a sense that when you have a game with incomplete information and with multiple stages, then sequential equilibrium allows you to use Bayesian updating and then rule out some equilibria which are not plausible. And to me, is also quite well known for a theoretical explanation of the chain store paradox. So this is a paradox where you have one big firm which has multiple stores in different cities, and then this firm actually tries to fight potential entrants in the different cities. So this is basically what you have observed, but the previous theory said that this is not what would go on in a subgame perfect equilibrium, and Krebs and Wilson challenged this and provided a very nice theoretical explanation for why the chain store paradox is not really a paradox, but why it can be explained with really mainstream economic theory. So to me, it seems that Wilson was good in bridging the gap between real-world observations that he made and, on the other hand, existing theory. And he usually focused more on the improvements of the theory side. So, and these often involved incomplete or imperfect information. I would also echo Rudolf a bit that definitely his work on auctions is not the only thing which earned him the Nobel Prize. On Milgram, you already heard quite a bit. Let me just mention 2 things. He's quite famous for his work on theory of the firm, together with Bengt Holmström, whom we have seen on the previous slide. And on one thing that is where also a lot of research is conducted at SBE, for instance, by Andy McKenzie and Jean-Jacques Herings, a paper on matching with contracts, which is at the intersection of auctions and matching models. To wrap up, both of them were very strong economic theorists. And quite interestingly, especially in our recent discussion at SBE, they won the so-called Golden Goose Award, which is an award that would recognize the tremendous human and economic benefits of federally funded research by highlighting examples of seemingly obscure studies that have led to major breakthroughs and resulted in significant societal impact. So the time span between they actually did their research, some of that even in the 60s and 70s, and the knowledge utilization in the form of spectrum auctions, for instance, 30 years later was enormous. And I think this nicely highlights the importance of being inclusive also to fundamental research and really not to always directly shoot for the application, but to be inclusive, to have both fundamental research and more demand-driven research at a university. Finally, I want to congratulate both of them and want to say that they are very well-deserved Nobel Prize winners. So thanks again to Rudolf for agreeing to do this with us, and of course also to Stefan, who explained very nicely the theoretical foundations.